Welcome, advanced developers and AI architects. Today, we are tackling one of the most ambitious topics in AI engineering, infinite prompting strategies. We will explore how to orchestrate tasks that require hundreds of sequential steps like massive refactors, deep research, or infinite component generation without manual intervention. We'll cover state machines, metaprompting, task budgets, and sub-agent orchestration. Let's get started. Let's begin by defining what we mean by infinite prompting strategies. At its core, infinite prompting is about designing agentic systems capable of executing long-horizon tasks, those requiring dozens or hundreds of sequential steps entirely autonomously. The basics involve shifting our mindset. We are no longer treating the LLM as a single-pass text generator. Instead, we are building a stateful, iterative loop where the AI reasons, acts, and observes continuously. Why is this necessary? Because real-world enterprise engineering, like migrating a massive codebase from Vue to React, requires hundreds of file reads, edits, compilations, and error corrections. A human developer cannot realistically babysit every single tool call. How do we achieve this? We bind tools to the model and place it inside a programmatic loop. In our deep dive, the critical difference is state. An autonomous agent persists a working memory, ensuring that the observations it makes at step 50 directly influence its architectural decisions at step 51, creating a continuous chain of execution. Take a look at this flowchart comparing the two paradigms. On the left, traditional prompting is a linear, stateless interaction. It stops immediately after the response. On the right, the infinite agentic loop represents our new reality. The initial goal kicks off a continuous cycle. The agent reasons, selects a tool, executes an action, and receives an observation. It loops back to reasoning endlessly until it determines the overarching goal is met, at which point it delivers the final output. To run an agent infinitely, we need a robust engine. Slide 2 introduces state machines and graphs. What is this? It's the application of finite state machines to LLM control flow. The basics involve using frameworks like LangGraph, where nodes represent your agent's logic, edges determine the transitions, and a shared state holds the conversation history. Why must we do this? Because if you let an LLM run for hundreds of steps using unstructured loops, it will inevitably get confused, repeat mistakes, or fall into an infinite hallucination loop. We need rigid rails. How is it implemented? We define a state object, create a node that calls the model, and use conditional edges to route to a tool execution node only when the model requests it. Our deep dive reveals the ultimate superpower of this architecture, recoverability. By attaching a checkpointer, the system saves its exact state after every single node. If a marathon task crashes at step 89 due to a network error, you don't start over. You resume instantly from step 89. This state diagram visualizes the beating heart of an infinite agent. From the start, we enter the agent reasoning state. If the agent decides it needs more data or needs to act, it transitions to tool execution. The tool runs and feeds the observation back into agent reasoning. Crucially, as noted on the right, the state is checkpointed at every transition. The agent bounces between these two states for as many turns as required until the task is complete. If an agent runs for hundreds of steps, it will generate a massive amount of text. This brings us to context survival using compaction and editing. What is it? It's a mechanism that actively manages your token context window. The basics are that long-horizon tasks, pulling in gigabytes of code and stack traces, will rapidly consume the LLM's memory. Why is this dangerous? If you hit the absolute limit, your API request fails, and your infinite task dies in its tracks. Furthermore, overloaded, messy context causes context rot, degrading the agent's logic. How do we survive? We enable server-side compaction. We set a trigger threshold, say 150,000 tokens. In our deep dive, we see compaction acts as an automated garbage collector. When triggered, the system pauses, generates a highly dense summary of the historical back and forth, drops the old raw messages, and injects the summary block. Your agent regains a massive amount of token headroom without forgetting its overarching mission. Look at this context management flow. As the infinite task is running, the system continuously monitors the state. Is the context greater than 150k tokens? If no, it loops back and keeps working. If yes, it hits the critical red node, trigger compaction. The system generates a history summary, safely drops old tool results to free up space, injects the summary block into the active memory, and seamlessly returns the agent to its task. To truly scale, we move from single agents to metaprompting and the infinite loop. What does this mean? It involves using a high-order prompt that instructs the LLM to act as a manager, dynamically writing new prompts for a swarm of subagents. The basics involve giving this manager a specification file and asking it to spawn isolated workers to handle massive workloads. Why is this necessary? Because a single agent's context window will collapse if you ask it to generate 100 unique, complex software components sequentially. How do we execute this? We can build a custom command, like Claude Code /infinite command, passing in our spec file and a target count. Our deep dive reveals the genius of this pattern. The metaprompt parses your inputs. The main agent then uses task creation tools to spawn exactly n parallel subagents. It writes a unique, hyper-focused prompt for each one. Crucially, each subagent operates in a totally isolated context, eliminating cross-contamination and context bloat. This mind map breaks down the metaprompt architecture. At the root is the metaprompt itself. It first parses inputs like the spec file and iteration count. Next is orchestration, where the main agent analyzes the goals and actually drafts the subprompts. Then we hit parallel execution, spawning subagent 1 through n in isolated environments. Finally, validation ensures the main agent reviews the generated artifacts and handles any individual worker failures. With great automation comes great risk. Slide 5 covers runaway protection, task budgets, and effort parameters. What are these? They are strict system controls that limit your resource consumption and control reasoning depth during long tasks. The basics involve setting a task budget a token limit across multiple turns and an effort parameter. Why are these mandatory? Because true infinite loops are financially dangerous. If your agent gets stuck trying to fix a broken unit test and fails 500 times, it will burn through your API credits instantly. How do we stop it? We configure the API request with a specific task budget, say 100,000 tokens. The sample code shows setting effort to high for deep reasoning. In our deep dive, distinguish this from standard settings. Max tokens only limits a single chat response. A task budget spans the entire multi-step workflow. Claude tracks this budget internally, and as it depletes, the agent will self-regulate and gracefully wrap up its work before hitting the wall. Look at the sequence diagram mapping the task budget lifecycle. The agent initiates the request with a total budget of 100k tokens. The Claude server returns a tool call, noting 95k tokens remaining. They loop back and forth. Eventually, a response comes back with only 15k remaining. The agent senses the low budget. Instead of starting a massive new subtask, it requests a final synthesis, safely delivering the output with 2k tokens to spare. Sometimes infinite prompting isn't about running continuously, but running persistently over time. Enter scheduled execution using the /loop command. What is this? It's a built-in mechanism that allows Claude to run prompts repeatedly or poll for status without you hitting enter. The basics are simple. You use the /loop command followed by an interval and a prompt. Why is this incredibly useful? Because developers spend hours babysitting CI/CD pipelines, waiting for deployments to finish, or checking for new PR reviews. How do you automate this? Just type /loop15m check the deploy status. Claude converts this to a cron job. Our deep dive is fascinating. If you type /loop with absolutely no arguments, it triggers a built-in maintenance mode. Claude will wake up periodically, review any pending PR comments, hunt for bugs on your current branch, fix them, and go back to sleep. You now have an autonomous teammate working in the background. This state diagram shows the life cycle of the autonomous /loop. The agent starts in an idle sleep state. When the cron interval is reached, it transitions to wake up and then execute prompt. Inside this state, it can autonomously check CI status, review PRs, and run bug hunts. Once complete, it evaluates the results. If action is required, it reports to the user. If everything is fine, it quietly returns to idle sleep. Let's bring this all together with a highly impactful real-time use case, generating 100 component variations. The scenario: your marketing team needs 100 distinct visual variations of a React hero component for a massive A/B testing campaign. The challenge: doing this manually or even using a standard AI chat session would take a developer days of tedious, repetitive prompting. The execution: we use the infinite metaprompt strategy we discussed earlier. The developer simply types /infinite at hero.spec.md at src/components/heroes100. The agentic flow is breathtaking. The main agent reads the spec file. It then orchestrates 100 parallel subagents. It gives each subagent a unique creative directive. The subagents generate the code in their isolated contexts and write the files to disk. The value here is undeniable. By leveraging infinite prompting orchestration, a task that required days of human intervention is completed autonomously in minutes. This flowchart visualizes massive parallel execution. The developer runs the /infinite command, and the main agent reads the spec. We hit the green orchestration node, spawn parallel subagents. The system dynamically spins up isolated workers variant 1 focused on minimalist design, variant 50 on cyberpunk, and variant 100 on corporate. Each agent executes concurrently and writes its final React component directly to the local disk. To conclude this masterclass, we must enforce best practices and governance. When building infinite agentic loops, you must enforce human-in-the-loop for critical paths. If your agent decides to drop a database or force push to main, your graph must pause and demand human approval. Next, implement deterministic judges. Do not rely solely on an LLM to verify if its code works. Use hard-coded unit tests to gate the loop. If the test fails, the agent must keep working. You must monitor token spend. Infinite execution scales costs infinitely, so always utilize the task budget parameter to protect your budget. Finally, scope your tools appropriately. A background agent doing research should never have write access to your source code. By mastering these governance rules, you transform AI from a simple assistant into a safe, autonomous software factory. Thank you for joining me. I invite all learners to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. See you there. Our final mind map encapsulates infinite mastery into 4 pillars. Governance requires human approval gates and strict tool scoping to prevent disasters. Safety relies on task budgets to control costs and context compaction to prevent memory overflow. Validation demands deterministic judges and unit test verification so the loop knows when to stop. And finally, scale is achieved through parallel subagents and accelerating your career at quicktechie.com.